Welcome everyone. Today I'm going to show you some examples of the ambiguous case of sine law, and I'm going to explain to you why we need to consider the ambiguous case of sine law in certain scenarios with non-right angle triangles. So when we have a non-right angle triangle or an oblique triangle where we're given specifically the information of two side lengths and one of their opposite angle, what can sometimes happen is that we get two potential triangles that could be created with this information. Now, we might also only get one triangle. In some cases, with this particular set of information, we might actually get 0 triangles that could be created. So let me show you the case where we would get 2 triangles. Let's just say, for instance, you have a triangle ABC where you're given the following information. You're given that side A has a length of 6 units, side B has a length of 9 units, and angle A measures 35 degrees. Now, in one case, let's just draw this out here. Second. All right, so let's say this is our angle A, that's 35 degrees. This is just a rough sketch. And this is going to be angle B and angle C. That makes this side B, that's approximately 9 units. And side A, that's approximately 6. This is side C, and we don't have a measurement for that guy. So this is one possible triangle that can be created. But if you imagine that there's a little lever here where side A gets to swing back and forth freely. So it can kind of swing out or it can swing back. There's actually a second triangle that I can create here by taking this side A and swinging it inside. So we're going to imagine that this green side has a lever up here and it can swing. Now imagine that I swing it this way. I can swing it and it's going to move all the way over here. And it can actually create another triangle inside here. And that's this triangle right here out of those same side measurements. So this will also be 6 units when it swings inside there. My picture isn't amazing. Maybe it's probably a little bit further inside to actually maintain that 6 units there. So probably more like this. So here's our second possible triangle right inside here. It still has the same measurements that were given to me up here, but it's an obtuse angle at angle B rather than an acute angle. So if I were to draw these two separately, this could be option 1 for my triangle here. And option 2 would essentially be the triangle that I drew where the green arm was swung inside. So there's my 2 triangles that I can create, and I'm going to show you maybe a better visualization of this in just 1 second. Okay, so that actually means that in this scenario, the angle B actually has the option to be either an acute angle, which is an angle between 0 and 90, or an obtuse angle, which is an angle between 90 and 180. It also means that angle C is a changing angle, and side C, the length of side C would actually be a changing side length. So here's a better visual of kind of what this looks like. Okay, so I said A would be 6, so let's just slide that to 6. Okay, so as you can see, that kind of side A is kind of like a swinging side where it has a kind of like almost like a little screw at part C or a fulcrum at part C where it kind of swings around. So you can see that this bigger triangle around this edge is our option 1. And then this smaller triangle where B is obtuse is our option 2. So here's option 1 and here's option 2. Okay, so what does that mean as far as what I said with you could get two possible answers, or maybe only one, or maybe none? So let's just look at this diagram one more time here. Let's say I extend the length of side A. Well, we can actually see here that if side A is longer than side B, there's actually only one triangle that can be created here. If I swing the arm, it actually swings outside of the triangle, and we can't actually have that. So this is one scenario right here. Now, if I make side A too short, look what's happening here. I actually can't, it doesn't even matter where I rotate this arm A, I actually can't create a triangle here. Now, if the angle is small enough, I can create a triangle, but if the angle is too big, it's actually possible that I won't be able to create a triangle that actually fits these certain measurements. So I'm going to show you the mathematical way that we can confirm this in this lesson. Okay, so the angle across from the extra side that we know, which in this case is side B. So we know angle A and its opposite side. In the scenario that I showed you, we know side B, but we don't know angle B. And so angle B is the angle that actually has two options to it. It has an acute option and an obtuse option. Okay, so how do we solve for both of these cases? Well, case one, we will use sine law as usual. And that's basically, we went over that in lesson 6. But basically we're just applying sine law in order to find the missing angle. And that's always going to give us the acute option. And in case two actually relates back to something that we learned earlier in this unit. And that is that I know that there are two angles when I use sine that could have positive ratios. And the first case is actually in the all quadrant. This would be what we get in case number 1 here. But we also know that there's another angle over here where sine could have a positive ratio, and it's in the sine quadrant. And it happens just before 180 degrees. And we know that these are, these two reference angles inside here are actually the same. So in order to calculate case 2, I actually want to take the rotation of 180 and subtract the reference angle that I would have got in case number 1. So the case 2 that we get is actually the obtuse angle that could fall in the sine quadrant between 90 and 180. So in order to calculate case 2, we will do 180 minus the acute angle that we get from case number 1. So a couple of little triangle rules that we want to remember when we're doing the ambiguous case of sine is that the sum of all the angles in a triangle needs to add up to 180 degrees. Another thing, because of that point from number 1, is that no triangle can actually have two obtuse angles. So it would only be possible for me to have a triangle that has one angle that's greater than 90 degrees. For the third point, this is actually kind of a new point for you guys, but when you do sine inverse, it can actually only be done on numbers between -1 and 1, or equal to -1 and 1, I should say. So if you have your calculator on you, I want you to try to do the sine inverse of something that's outside of the range from -1 to +1. Let's say we try to do the sine inverse of something like 3. You're going to notice that you actually get a math error on your calculator, and we'll learn a little bit more as to why this is in the next unit. But you should know, just for your solving process, that if I go to take the sine inverse of something that's outside the range of -1 to 1, it's actually not possible. And this is actually going to come up when we have those scenarios when we have triangles that actually aren't possible to create. So this scenario right here, when I go to do sine inverse, you're going to notice you're taking sine inverse of a value that's not between -1 and 1, and that should tell you that you actually have this scenario where the triangle can't be created. Okay, and then the last one is that sine gives a positive answer in quadrant 1 and also in quadrant 2, and I explained that up here, and that's why we get a case 1 and a case 2 in this scenario. Okay, so let's take a look at an example here. What's very helpful in these questions as well is if you actually have a ruler, and if you happen to have a geometry set at home that has a protractor in it, you could actually create a scale diagram of this. Now, it might be a little bit hard to create something that's 12 centimeters and 17 centimeters, but if you maybe let 1 centimeter on your calculator equal half a centimeter here, or 2 centimeters here, I should say, you can create a scale diagram, and you can use your protractor to actually measure the angle 21 degrees. This just helps you figure out if you actually can have a triangle that gets created out of this information. Now, if you don't, you're just going to use, do your best to create a diagram. What I like to do always is I will place the angle that I know in the bottom left corner. And that means that this side right here will kind of be the changing side. And I always put the angle that's across from the extra side that I'm given over here. Okay, so here's what we know. We know that side B, which is across from angle B, is about 17 centimeters, and this should be about 21 degrees. So try to make that around 21 if you can. And this will be side B. We're going to let that be 17 units or 17 centimeters. And then side A will be about 12 centimeters. So it's going to be shorter than side B. Do your best. Okay, so like we talked about before, this is the scenario where we have side A, the length of side A that's across from the angle that we know is actually shorter than side B. So here's what we can do with the second triangle. If we imagine that this arm can swing, I can actually swing it inside, and I'll have another triangle that gets created with that arm swung inward. So here is case 1, and case 2 will be the same rotation, but the arm's going to be swung inside this time. So this is going to be our side A here. Okay, and if you happen to have a protractor, you can actually do an even better job than what I'm doing here in drawing this. Okay, so I'm just going to erase these extra little things. And the final angle here is angle C, and its opposite side is side C. This is going to be the diagram for case number 2. Okay, so our job is to find angle B. So angle B in case 1 is acute, and angle B in case 2 is obtuse. So let's just focus on case 1 for now. This is our usual case for sine law. Nothing new here. This is what we reviewed yesterday. This is what we learned about in grade 10. So I'm going to set up sine law. And one thing that I want you to remember here is that sine law can be set up this way. But if I'm looking for an angle, I can also flip both of these fractions. And as long as I flip both of them, the ratio still remains intact. So that's actually what I'm going to do for these cases, because I'm trying to isolate for an angle, and it's just easier to isolate for the angle when it's in the numerator rather than the denominator. So we're going to use sine law, but flipped upside down. Okay, so let's plug in what we know. We know angle A, side A, we don't know B, and we know side B is 17. Okay, so in order to get sine B by itself, I'm just going to multiply up 17 on each side. And we get that sine B is equal to this ratio here. So if you plug this into your calculator, make sure you're in degree mode. And you're going to plug it in, and you should get something that's around 0.507687. Okay, now leave this in your calculator. We don't need to write it on here because we're just going to leave this value right in our calculator, and we're going to do sine inverse of that answer that we got from plugging in 17 sine 21 over 12. Now, you should notice as well that if this value right here is 0.507687, and so on, 688 we'll say, this is a value between -1 and 1. So remember, we talked about up here how you can't take the sine inverse of values that are not between -1 and 1, and this value is between -1 and 1. So we should get a value when we put that into our calculator. So sine inverse of your answer there, and that should give you about 30.5 degrees. Okay, try to follow along with your calculator so that you know how to plug it in. Okay, so this is case number 1 for angle B. Now case number 2, so remember this is what we just did. We just did sine inverse of a positive value. We know we can have answers in the all quadrant and also in the sine quadrant. So if this is also 30.5, I can find the obtuse option for that by doing 180 minus 30.5. So case number 2 is going to be the case where we simply calculate angle B by doing 180 minus case number 1. Whoops, I meant to enter in case number 1 there, 30.5. Great. So we should get 149.5 degrees for our second option for angle B. Now, what I always like to do in these scenarios here is double check my findings by making sure that angle C in both of these cases, or at least in case 2, is a possible angle, because sometimes there's only one triangle that can be created, but we don't know that until we check angle C for case number 2. So angle C for case number 2, if I look at my diagram here, if I found case number 1 to be 149.5, and I know this angle of 21 degrees, angle C should be 180, subtract those two things. So subtract 21 degrees and subtract 149.5 degrees. So if you do that in your calculator, you're going to notice that you get an answer of 9.5 degrees. As long as this is a number that makes sense, like it's an angle measurement between 0 and 90, this should be an acceptable answer, which means that this is an acceptable case. Now, if you check this and you get something like -10 degrees, well, negative degrees doesn't quite make sense, and that means that we would actually discount the entire case 2. So just something to look out for, to do a little check to ensure that case 2 is a possible case. Okay, and the rest of this actually asks us to find angle C anyways. So we're going to just continue along with case number 1 and case number 2 for part B. Part B I already did for angle C above, so I'll just rewrite it here. So that was 9.5 degrees. And case number 1, if we input what we know now, I have 21 degrees and 30.5 degrees, and I'll find angle C by subtracting those two from 180. So we're going to do 180 minus 30.5 minus 21. So you can enter that into your calculator quickly here. And you should get an angle of 128.5 degrees. Okay, so now that we have those angle measurements, we should also be able to find the remaining side C, which is a changing side. So you'll notice that side C in case number 1 is actually much longer than side C in case number 2. So we're going to get 2 different answers for those. So if you'd like, you can enter in your answers from part B, just so you have them in your picture. And then we're going to set up sine law. I'm going to use this angle and side opposite pairing that we were given in the initial question, and then we're going to use sine law to find angle C. So because I'm trying to find side C, I'm going to use A over sine A equals C over sine C here. Now this is going to be the same for both cases. This will be 12 over the sine of 21 degrees. And this will be c over sine of 128.5. Now for case number 2 over here, we're going to set up the same thing, except I'm going to use case number 2's angle C. So in both cases here, in order to calculate side C, all we need to do is multiply up the sine of the angle here. And then we'll plug it into our calculators. Okay, so this is going to cancel over here. And you can enter this in quickly into your calculator. Let's round to 1 decimal place here. You should get 26.2 centimeters for the first calculation. Okay, then you can enter that into your calculator for the second calculation here with sine of 9.5 multiplied up here. So these will cancel. And then just enter into your calculator. Okay, again, round to 1 decimal place, you should end up with about 5.5 centimeters as your answer for case number 2. Okay, just as we suspected, this side is much shorter than the other option for side C. Okay, let's look at another option here. In triangle ABC, side A is 4 centimeters, side B is 14 centimeters, and angle A is 60 degrees. How many solutions for angle B are there? 1, 2, or none, and solve if possible. Okay, so let's take a look. Now, if you had a ruler here and a protractor, you could create a great diagram. I don't on here, but I will just do my best. I've got a 60-degree angle and a 14 centimeter side here. So as I said, I like to let the angle and side combo that I know be this angle down here and this side over here. And then the additional side that I know, I like to put its angle down here. And that means that the side that I know will be over here. So here's side A. Now I'm thinking, I don't know this for sure because I'm not doing an exact scale diagram, but I'm thinking we're going to end up with something like this, where we have a side kind of just hanging here and no real triangle that can be created. If you have, if you check out GeoGebra and you just put into Google ambiguous case of sine triangle creator, you might find this link for GeoGebra, and you can check this out as well, just to double check. But we can also tell by the math that we have as well. So I'm going to show you guys how to do that, but I'll just show you kind of what we have here. So B was 14, A was 4, and it's not quite in the screen here, but you can basically see that there's really no triangle that's going to be created out of this information. It's much too big of an angle and too big of a side length there. Can't quite get 60, but you kind of get the idea. All right, so what's going to happen when I try to sub this into my calculator? Let's say I go ahead and I try to solve for case number 1, where I have A, let's do sine A on top, and side A on the bottom, and then sine B over side B. Here's what we have. Sine 60 over 4 equals sine B over 14. Now, just as we did before, what we need to do is multiply up the 14 on each side. And I want you to calculate this number in your calculator here. So take a second to do that. 14 times the sine of 60 over 4. Okay, so I got a number that's about 3.03109, let's say, rounded. Now, remember, I can only take the sine inverse of values between -1 and 1. Is 3.031 in between -1 and 1? It's not. So if you go and you try to do the sine inverse of this value in your calculator, you're actually going to find that you get a math error. So if you have it in your calculator now, do the sine inverse of your answer. and you're going to see that you get math error. And that is actually the mathematical way of the math telling you that this triangle is actually not a possible triangle that can be created. So there's actually no cases in this scenario where there's solutions for angle B. Okay, so we're going to say no solutions for angle B. And in brackets, I'm just going to say triangle is not possible. Okay, let's take a look at one last example here. So in triangle ABC, angle A is 40 degrees and sides A and B are 22 centimeters and 12 centimeters respectively. How many answers are there for angle B? 1, 2, or none? Now, a lot of times in order to figure this out exactly, we need to do the math to kind of decide. So here's kind of what we know. I'm going to put angle A, which is the side that I know, and the angle that I know in that corner. And then we're going to have side A, which is pretty long compared to side B. So something kind of like this. Okay, so if we've drawn this visually somewhat correctly, we can kind of see that even if there is an option for this arm to swing inside, that even if I swing it as far as I can, it's still going to be way too long to create a second triangle here. There's also a quick little cheat way to figure out whether there's two possible triangles versus one. The only way that you can figure out if there's none is to do the solving process, but I know that there could be 2 or 0 as long as side A, or the side across from the angle that I'm given, is shorter than the additional side given. Now, if the side across from the angle that I'm given is longer than the additional side given, there will always only be one possible triangle that can be created with that information. Now, if that's difficult for you to remember, what you could try is to calculate case 1 and to calculate case 2. So this goes back to something that I discussed earlier. So I'll touch on that again once we do the calculation here. Okay, so let's say we set this up again with sine A over side A. Just going to zoom in a little bit here for you. And sine B over side B. Plug in the information that you know. And multiply the 12 up. So when you put this into your calculator, you will find that you do get a value here that's between -1 and 1. So we know we can only take the sine inverse of values between -1 and 1. And we get here, just plugging it in, 0.3506 and so on. So you're going to do the sine inverse of that value in your calculator. Leave all the decimals, or if you need to, write it down and try to enter it in separately. Just make sure you leave a good amount of decimals. So here I'm getting 20.5 for angle B. Now, when you go to calculate case 2, at first glance, it's going to seem like case 2 is actually a possible case. So I'll show you what I mean. If I went to calculate case 2 here, I know that the second option for angle B is 180 degrees minus the case 1 findings. So this is possible. It's going to give me 159.5. So how do I know that this is not a possible case? And it goes back to this little check that I told you to do. And that check says that if angle A is 40 degrees and I get angle B as 159.5 degrees, let me just write that underneath instead. Whoops. Sorry. And I get B as that 159 that we just calculated. what would angle C be? Well, angle C is 180 minus the other two angles. So let's see what happens when we subtract these from 180. Well, what's going to happen here is I'm actually getting a negative answer. I get negative 19.5 degrees. And we know that getting a negative angle is actually not possible, which means that the entire case 2 is not a possible case. So we actually don't have a case 2. We only have one possible triangle that can be created here. And that's where angle B is 20.5 degrees. So just as a little summary for you guys, the only time that we would consider that there could be a potential ambiguous case or second triangle that could be created is when we have a non-right triangle and we're given the scenario where we are given two of the side lengths in the triangle and one of their opposite angles. This is the scenario where we would have to consider that there could potentially be 0 triangles, 1 triangle, or maybe even 2 triangles. So if the side across from the given angle, so the side opposite to the angle that's given, is shorter than the additional side length, then there are either 2 triangles or maybe even 0 triangles that could be created. So examples 1 and 2 give a good idea of this, of what this looks like. So in this scenario, the side across from the given angle is shorter than the additional side length given. In this case, there's 2 triangles that can be created. But let's say side A was really, really, really short. That's example 2. Example 2 says that if the side across from the angle given is shorter than the additional side, then sometimes there can be 2 triangles, but if it's too short, then there's actually 0 triangles that can be created. And finally, if the side across from the given angle is actually longer than the additional side length given, there's actually only going to be 1 triangle that you'll need to be considering, and that would be like in example 3. So we can see here that A is across from the angle that's given, and this side length is actually longer than the additional side length that's given. And as we can see here from our picture and from the math, there's only 1 possible triangle that can be created there. So if you want to write this little summary in your notes, you can pause the video. This is just a helpful way to kind of predict whether you have 1 case, 0 cases, or 2 cases that need to be considered when you're doing the math for these triangles.